Hello, and welcome to my presentation about cosine similarity preserving dimensionality reduction of dense embedding vectors. First of all, I'd like to apologize for the difference in the name between the presentation and the website, because on the web you might see it written down as cosine similarity preserving compression of dense embedding vectors, but this is incorrect. Here we'll be dealing with dimensionality reduction. I am an assistant at Małopolska Center of Biotechnology and a computer science student at Jagiellonian University. I'm currently writing my master thesis. My research topics focus on NLP and information mining, but I also research algorithms for metagenomic analysis and general tabular learning. In fact, you'll be able to meet me at a poster session of the microbiome track. The first question that comes to mind is, why should we even bother with this problem? And, well, once you extract some info from a text, there is a high chance that you want to use the vector embedding or the text embedding as a representation for it, because it is one of the most commonly used forms of representation. And this is because there is a very standardized way of comparing the semantic similarity of embedding vectors, and this is the cosine similarity. The problem with vector embeddings is that, well, handling them is problematic. A vector comparison is slow and they require a lot of storage for indexing. Our database's usefulness is proportional to its size, but well, so are the processing costs. And by costs, I don't mean only monetary costs that are connected with keeping large storage, but also the time cost that we'll need to first index and then query the database. There are many ways of mitigating this problem, but they are unfortunately not enough, because even the most commonly used algorithms, like the approximate nearest neighbors, they reduce the number of comparisons, of vector comparisons that we will need to do. But, well, at the end of the day, we still need to do them. And if you take a look at the expanded cosine similarity equation, you'll notice that, well, it is the number of computations that we need to do is proportional to the length of the vectors. So an obvious answer, or an obvious proposition of answer, is that we'll be able to reduce the number of operations if we cut down on the length of the vectors. And on top of that, well, this way we'll also reduce the storage that we need. So okay, now that we have a proposal of the answer, there are still a few questions that we need to tackle. The first one of them is, how exactly should we do it? Because, well, the most commonly used dimensionality reduction techniques, they are designed to handle Euclidean distance, not cosine. So we need to find the best way. Then, well, as a wise man once said, there ain't no such thing as a free lunch. We cannot gain anything for free. We need to trade off something. So we need to check what exactly do we trade off and how much do we trade off for the bonuses that come with shortened vectors. And the third question is, how much should we scale them down? So how many dimensions can we cut off before the vectors start being, well, useless? The rest of the presentation is divided into two sections: methods and results. We'll talk about the datasets that we will use for assessing the applicability of our dimensionality reduction methods and the metrics that we will use for those datasets. Then we will talk about the specific framework that we will use for dimensionality reduction and what exactly algorithms did we test. As for the results, we will of course talk about the performance of on the datasets, and not only about the metric the precision and other metrics like that, but we'll also talk about the server performance and how much time and storage do we save. But also we will tackle the topic of generalizability. So what is the chance that we'll be actually able to apply those results in the wild? So let's dive into the methods. The first dataset that we'll be using is the Microsoft marker. It is commonly used for the assessment of the semantic similarity task because it is a dataset that is composed of multiple triplets. And of the triplets, the first one is an anchor or a query. So it is a word or a short sentence that is connected to some specific topic. The second part of the triplet is the positive sample. So a short text that is connected to the same topic as the anchor or as a query. And the third element is the negative sample, so a text that is irrelevant to the topic. The metrics that we'll be using for this dataset is accuracy, which we will define as the percentage of triplets in which the embedding of the positive sample is closer than the negative to the anchor. We will use MS Markup to assess the performance of our all of our dimensionality reduction techniques. And then once we understand their overview, we will select the three best and apply them to the PubMed/Medline dataset. PubMed dataset, or our PubMed dataset, consists of 60,000 publications that can be either relevant or irrelevant to a specific query, one of 70. So our task here is the information retrieval about, and I will say more about it in a little while. We will keep our publications in an Elasticsearch database, and this way we will be able to actually assess the performance of our algorithms on a real-life setup. So we'll be able to measure the indexing and querying time as well as the storage that is required to storing it. The metrics that we will use for the PubMed dataset, well, there are two of them, because first of all, you need to keep in mind that it is not a classification problem, it is information driven. So we don't have a set of publications that we want to assess whether they are connected to the query or not. We want our algorithm to rank all of our, or the top n of our publications in the order of diminishing probability that they are actually connected to the query. So the first metric that we'll use is recall. And here it is defined as the number of publications relevant to the topic that we do find in our top n results, divided by the total number of all relevant publications that we have in our database. The second metric that we'll use is the mean average precision. So it can be seen as average precision at seeing relevant documents. And its main purpose here is that it penalizes incorrect ranking. So the reduction framework that we will use looks like the scheme on the slide. So we won't be reducing the whole vector. Instead, what we'll do is, starting from the text that we want to vectorize, we'll first put it into a language model to obtain the text embedding V. And then we will reshape the text embedding into, well, a larger number of small vectors, which will then reduce dimensionality of in separate of the others. After reducing their dimensionality, we'll concatenate them and reform them into our reduced vector V'. The algorithms that we will evaluate are as follows. Many of them are the traditional dimensionality reduction techniques that are commonly used, like PCA, UMAP, whitening, or locally linear embedding. We'll also use simple averaging, so that if we, for example, split our vector V into parts of the length 8, then after we'll average them into a single scalar. Another method that will be used is the autoencoder based on the deep learning. So a set of encoder that is reducing the dimensionality of V into V', and a decoder which will try to again expand V' into V, so that the cosine similarity between V and decoded V is as high as possible. And another addition of deep learning that we'll be able to use is the Siamese network. Siamese network is a deep learning algorithm which aims to create semantically meaningful embeddings, so that the embeddings of two similar sentences have lower cosine distance than embeddings of two dissimilar sentences. In addition to the triplet loss that is commonly used for training this algorithm, we are also using variance loss introduced by Adrian Birds et al. On this year's ICML. Siamese network is the only supervised algorithm out of the ones that we'll be assessing. So now let's take a look at the results. The first dataset is the MS marker, and here we can see that there are two clear leaders, PCA and the Siamese network. The results are, well, I'd say surprisingly good, because it looks like the Siamese network is able to retain up to 94.2% accuracy, even if we reduce the number of dimensions by 24. The three candidates that we will use to assess, use to assess our methods on the PubMed dataset are the Siamese network, PCA, and the simple averaging. And on the graph to the right, you can see how do the accuracy diminish on the linear scale. As for the PubMed, we'll first look at the server performance, and we can see that we stop getting better after 24 times reduction, but once we get there, the results are still, again, surprisingly good, because we managed to cut down the indexing time down to 1/3, the amount of used storage by down to under 20%, and we are able to speed up the query by over 5 times. So now if we take a look at the PubMed information retrieval metrics, we can see that the model that we have been using so far, the all-MPNet based V2, is behaving pretty much as expected. It is worse than on the MS Marco dataset, but well, the task is also more difficult. From the graphs you can see that if we stick to the 4 times reduction rate, we are able to retain 95% mean average precision and about 90% of the original recall. And as for the generalizability, the row on the bottom shows you what happens if we apply exactly the same methods to completely another model. So to the BioBird SNLI, multi-NLI STSB, which has been trained on completely another dataset and consists of completely another vocabulary. So we can see that the results are pretty similar to what we experienced with the base model. So we can say that our methods should be generalizable also to other cases. So now, as for the recommendations, I think that the best choice, and if you want to play safe, the best choice is the 4 times reduction, because if you use it, you can still retain over 95% of the original mean average precision. So the difference is maybe not negligible, but hard to notice. And 90% recall, but you are able to speed up the query over 3 times and reduce the amount of storage by 2.8 times. And if you dare to go higher, you can use Siamese network by over 60 times reduction, although the metrics are diminishing pretty quickly. Thank you for your attention.